Agostini. He was and at the theoretical division of the Los Alamos laboratory. And then he joined the Fermi theoretical astrophysics group, becoming head of the group and subsequently director of the Particle Astrophysics Center. He is professor at the University of Chicago since 1986. He has been chair of the Department of Astronomy and Astrophysics, dean of the Physical Science, and now director of the Kablan Institute for Cosmological Physics, which the University of Chicago hosts. Rocky has been also chair of many panels and committees, including the Dark Energy Task Force, which has played a pivotal role in establishing the observational efforts towards dark energy. Rocky has been and still is a pioneer of the connection between particle physics and cosmology. He's authored more than 200 articles, and he has received many awards, including the Hyman Prize for American Astronomical Society and Award for Excellence Teaching from University of Chicago. He is also co-author of, with Professor Mike Turner of the Early Universe, the most popular textbook of cosmology, which has led many of us in the subject. So it's a great pleasure to have Rocky here talking about gravitational particle production in the early universe.
Thank you, Fabio. Thank you. And it's a pleasure to be here in Bologna again. I was trying to remember if this is my third or fourth time in Bologna, one or the other. Since I'm a cosmologist, 3 and 4 is approximately the same number, so it's okay. So this is a photo of Bologna. Is that right? I wasn't quite sure when I got it on. So the title of the lecture today is Gravitational Particle Production in the Early Universe. As a little bit of background, I tried to work over the years at the interface between inner space and outer space, particle physics and cosmology. And I believe this goes both ways, that particle physics is important to understand astrophysics in the universe, and the universe is a laboratory for particle physics. So using particle physics to understand the universe, today I will mention dark matter. It's also, of course, used for the study of dark energy, the baryon asymmetry, neutrinos and explosive events, CMB fluctuations, and if you're interested in the growth of structure, particle physics is a way to produce the seeds that grow into structure that we see. And on the other side, to use the universe as a particle physics laboratory. In particular, using what I'm interested in today is using the high temperatures of the early universe to learn something about particle physics beyond the scale that we could learn in terrestrial accelerators. The universe also provides a laboratory for very long lifetimes of particles and very long path lengths. And it's used also in placing limits for beyond the standard model physics. Stellar energy loss plays a role in limiting particle physics models. There are large magnetic fields in the universe that are used, and of course, CMB fluctuation tell us something about particle physics. So here's a brief history of the universe in several movements, starting with a movement of Planck strings. And this would be a string dominated. So some of my friends are string theorists. Well, I don't have any friends who are string theorists, but I know people who are string theorists. And they tell me that the very early universe started dominated by fundamental strings. And probably sometime around the Planck time, 10 to the minus 43 seconds. I don't know if we can associate a temperature to this string dominated phase. And the relics of this phase is somehow a universe that started in 11 space-time dimensions, ended up with a universe with only 3 spatial dimensions. And it's unclear why. I will talk about, so the lecture today will concentrate on the vacuum energy or inflation phase and the transition to a matter-dominated phase. The temperature during inflation is approximately h over 2 pi, the expansion rate over 2 pi. And this produced CMB fluctuations, perhaps primordial black holes, gravitational waves as seeds of structure, and perhaps dark matter. So there are a lot of relics from this phase that we can look for today. Then the universe transited from an inflationary phase, presumably to a matter-dominated phase. And perhaps that's where dark matter was produced, perhaps the baryon asymmetry. Then went into a radiation-dominated phase with dark matter, light elements, baryon asymmetry as the relics of this phase of the universe. Then it went to a matter-dominated phase, growth of structure. And finally today, starting roughly the day before yesterday, it seems to have recycled into a vacuum energy or inflation phase, the acceleration of the universe. So I will work mostly in this yellow region. So I will study and talk about an inflationary phase, which is a quasi-de Sitter phase. It's not exactly de Sitter phase, but it's close to it. So a quasi-de Sitter phase of inflation, which transits to a matter-dominated phase when inflation ended, and then eventually produced a radiation-dominated phase, which we can actually call the start of the hot Big Bang. So inflation, we usually imagine, is the universe dominated by the potential energy associated with a scalar field. We don't know the origin of this scalar field, what it has to do with fundamental physics, but there's a really nice name for it, a really cool name. And if you have a nice name, people think it's okay. It's called the inflaton. So the inflaton is the particle whose vacuum energy dominates the energy density of the universe. And I'll talk about quantum fluctuations in the inflaton, which produce the temperature and density inhomogeneities, the temperature inhomogeneities and anisotropies, which are studied in the CMB, and the density inhomogeneities, which end up being the seeds of structure. The evolution of inflation is determined by the inflaton potential. There's some potential for the inflaton field. During inflation, the inflaton slowly gains kinetic energy, and eventually the kinetic dominates the potential and inflation ends. At the end of inflation, the universe is frozen in a low entropy state with the energy in the zero momentum mode of the inflaton field. After the end of inflation, the energy is in an oscillating inflaton field, which leads to a matter-dominated expansion. And sometime, possibly much later, the inflaton decays into radiation, and this really is the start of the hot Big Bang. The start of the radiation domination is characterized by a reheat temperature, which is the maximum temperature of the radiation-dominated universe. So there is a standard inflationary picture, but there is not a standard inflationary model. What we don't know, there's a long list of what we don't know. This is a partial list. We don't know who is the inflaton. Where does this field come from? What is the inflaton potential? Is there only one inflaton? Now, so far, particle physicists have discovered one fundamental scalar field, the Higgs, and have spent a lot of effort and energy and money looking for other scalar fields without success. Perhaps there's only one scalar field in the universe, but perhaps not. Why only one inflaton? We don't know the expansion rate of the universe during inflation, h sub I. We don't know the expansion of the universe at the end of inflation, h sub E, but there's a popular choice that we take as sort of a fiducial value of 10 to the 12 GeV. We don't know the duration of the inflaton oscillations. for the matter-dominated phase. We don't know what the reheat temperature is, the maximum temperature of the universe after inflation. There's a popular choice of 10 to the 9 GeV, motivated by really nothing, but it's a popular choice. And presumably the reheat temperature, it has to be larger than 100 GeV in order for a baryon asymmetry to be produced. Now, if we use the temperatures of the early universe to produce particles that we can study, the mass, we can't use thermal processes to produce particles of the mass larger than the reheat temperature. And this is where gravitational particle production can play a role. So cosmological gravitational particle production is the idea that an external field can create particles from the vacuum. This was first proposed or pointed out in a largely forgotten paper in 1939 by Schrödinger. People have heard of Schrödinger, but this not of this paper, I imagine. I'll mention a little bit about this paper. And so he was the first person to point out that just the expansion of the universe can produce particles from the vacuum. And in another application of producing particles from the vacuum, it was something known as the Schwinger effect, named after Julian Schwinger in 1951, who pointed out that just in quantum electrodynamics, the vacuum is unstable to the creation of particles. And creation of particles in an external field was also the basis of Hawking radiation from black holes. I will concentrate on time-dependent gravitational fields, in particular the Big Bang. And again, I have this model where there's a quasi-de Sitter phase, inflation, followed by a transition to a matter-dominated phase, then a radiation-dominated phase. Now, gravitational particle production is an application in a use of quantum field theory in a classical gravitational background. This will be a semi-classical discussion where there will be a quantized fields in a classical gravitational background. So the gravity will not be quantized. My quantum theory of gravity is not quite ready to tell everybody about. So it will be classical GR. And my motivation is to explore whether gravitational particle production can be the origin of dark matter and whether it can provide cosmological constraints on beyond standard model physics. So I mentioned Schrödinger's paper. This was written in 1939. The title of this paper is The Proper Vibrations of the Early Universe. I think it was a really amazing insight and a brilliant paper that Schrödinger forgot about once he wrote it. He never referred to it. And in fact, it was forgotten. There was something going on in the world in this period, 1939 to 1945, that people didn't pay too much attention to particle physics and astronomy. But recently, this was a strange citation history that for the first 50 years, no one paid attention to this paper, and now suddenly people are paying attention to it. So in the last year, it's had about 150, last decade, about 150 citations. Probably 145 of them are from me. Is that true? So anyway, this is the proper vibrations of the expanding universe. And what Schrödinger pointed out is that just the expansion of the universe creates particles. So this was, I think, a great conceptual insight. There are technical problems with the calculation. You really need a quantum field theory approach to do the calculation. And Schrödinger, this was 10 years before quantum field theory was really established. He knew something about quantum mechanics. He just used quantum mechanics. And he came to some incorrect conclusions. One of the incorrect conclusions had to do with the birefringence of light. He didn't realize that the photon is conformally coupled to gravity, so you don't produce photons or do anything with photons in this effect. He also thought wrote that he was alarmed by this result, that the expanding universe can create particles. He used the word alarming all the time. I think he thought it was some fundamental flaw in either quantum mechanics or general relativity. He looked for and found a expanding universe solution where there is not particle creation. And he discovered something that later became known as a Milne universe, which essentially is a slice of Minkowski space. So what else can I say about this? Maybe that's enough. So let me explain a little bit how disturbing the quantum vacuum can lead to particle creation. So we know because of quantum mechanics that if we look at space on sufficiently small scales, there are quantum fluctuations in fields due to the uncertainty principle. So I don't know what this movie illustrates, but it looks pretty cool, right? You know, it's the idea that, you know, if you look at space on small enough scales, particles are coming in and out of the vacuum. And the thing that's familiar to many people is the idea that a strong enough electric field can lead to particle creation. So this top image just shows an electron and positron coming out of the vacuum and then going back into the vacuum. This is happening all the time because of the uncertainty principle. But in the presence of an electric field, as an electron and positron comes out of the vacuum, the electric field will accelerate the electron in one direction and the positron in the other direction. And what was realized back in the 1930s by Sauter and Heisenberg, et cetera, is that, and Weisskopf, that this could lead to particle creation. And the final calculation was done by Schwinger in 1951. It's the usual statement that a phenomena is named after the last person to calculate it. So what Schwinger did is the calculation, and he realized that you would have particle creation if the energy gained in acceleration from the electric field over a Compton wavelength of the electron exceeds the electron's rest mass. So the only dimensionful quantity in the problem is the mass of the electron. So the critical electric field is the electron mass squared. And you can put in the C's and E's and H bars if you wish. And this turns out to be 10 to the 16 volts per centimeter. So here's a prediction. If you go in the laboratory in the basement and produce an electric field of 10 to the 16 volts per centimeter, you're going to produce electrons and positrons. People must have voltmeters in your laboratory because it doesn't go up to 10 to the 16 volts per centimeter, right? That's a pretty difficult electric field. So what Schrodinger realized is that the vacuum, the QED vacuum, is unstable and it will decay e to the minus pi critical electric field divided by the actual electric field that you have. So this is a prediction that's hard to measure by producing electric fields, but it's possible that magnetic fields, that you can produce these electric fields in high power lasers. This was the cover of a Nature article back in 2007. And if you can't read what's written there, it says physicists are planning lasers powerful enough to rip apart the fabric of space and time. Very violent. These laser people are so violent, ripping apart the fabric of space and time. And Gerard Moreau, who won the Nobel Prize, shared the Nobel Prize for the development of high energy lasers, said we're going to change the index of refraction of the vacuum and produce new particles. So just doing, again, dimensional analysis, if you ask what is the intensity of a laser that has the critical value of the electric field for particle production of electrons and positrons, it's 10 to the 30 watts centimeter squared. And that's a pretty large magnetic field. But as we seem to be marching off. This is the intensity in watts per centimeter squared as a function of time. And you talk about light materialization, producing electrons and positrons from the Schwinger effect, sometime around 2030. And 2030 would be a very exciting time. Lightbird will be launched. We're discovering new particles at the LA. Everything's promised in the next decade. So it's very difficult to do these things in the laboratory to produce these high electric fields, high magnetic fields, but the universe is a laboratory, right? So perhaps there are large magnetic fields, say around magnetars or Crab, that can produce magnetic fields large enough to see the Schwinger effect. And again, it's so violent, ripping the iron out of your blood from 1,000 miles away. That sounds pretty violent. So if you think of a critical magnetic field associated with the critical electric field, it's about 5 times 10 to the 13 Gauss. That's about the magnetic field in the Crab, and is smaller than the magnetic field we think associated with magnetars. So strong magnetic fields imply the existence of strong electric fields. There are unexplained phenomena that's not understood, at least by me, associated with pulsars and magnetars, et cetera. Perhaps this has something to do with the Schwinger effect. Okay, so this is an example of particle creation in an external field, in this case, an electric or a magnetic field. A tidal gravitational field can also lead to particle creation. And again, particle creation of energy gained and acceleration from gravity over a Compton wavelength exceeds the particle rest mass. And this is a way of thinking of Hawking radiation. Okay, so now what Schrodinger realized is that you could have the same thing in the expanding universe leading to particle creation. Again, particle creation of energy gained and acceleration from expansion over a Compton wavelength exceeds the particle rest mass. So particles will come out of the vacuum due to Heisenberg's uncertainty principle, be caught in the expansion of space. And if the expansion rate is large enough, larger than the rest mass of the particle, then you can produce particles from the vacuum. So the critical expansion rate is related to the mass of the particle. So in 1939, Schrodinger wrote in his paper, generally speaking, this is a phenomenon of outstanding importance. With particles, it would mean the production or annihilation of matter merely by the expansion. Why would that be of outstanding importance? If Schrodinger thought it was outstanding importance, why did he never do anything with it? Completely dropped it. It was forgotten in the 40s, 50s, and 60s by Schrodinger also, and it wasn't really picked up again till the work of Lenny Parker in the late 60s. He was a graduate student at Harvard, and Sidney Coleman said, why don't you look at this thing that Schrodinger did a long time ago, and Parker is responsible for the rebirth in this. In his 1968 paper, he wrote, for the early stages of a Friedmann expansion, particle creation, may well be of great cosmological significance, especially since it seems inescapable if one accepts quantum field theory and general relativity. He said, this is of great cosmological significance, and you keep looking through the paper, so why is it significant? And you don't find it. So people sort of realize this might be interesting, but what would be its application? The first attempt at an application was made by Zeldovich in the early 70s, who proposed this as a way to understand why the universe is homogeneous and isotropic. This was a brilliant idea that didn't work. We now understand the homogeneity and the isotropy of the universe due to inflation. Okay, so this is Schrodinger's alarming phenomenon. There was other interest in gravitational, that should be GPP, in the early 70s, mostly regarded as a curiosity. And people in the US, people in the Soviet Union, there was cosmological gravitational particle production, CGPP, in the CCCP, in the UK, etc. But the real great cosmological significance was not realized until the early 80s, largely by the work of Mukhanov and Shipyshov, who realized that the gravitational particle creation during inflation produced the inhomogeneities and the seeds of structure. Well, could there be more? Gravitational particle production is universal. As Parker said, it's inescapable. Now there's some lawyerly, you don't have lawyers in Italy, do you? But in the US, there are lawyers and they always make you put in the fine print. You have to violate bioconformal symmetry. It's universal. Gravitational particle production is not a large effect. And you can think of the CMB perturbations as 10 to the minus 5, so maybe 10 to 30 parts per million. What else could be observable? Dark matter could be used to produce dark matter, could be used to produce CMB isocurvature perturbations, non-Gaussianity, and maybe it's related to the baryon asymmetry. So here's a map I'm going to follow. In Minkowskian quantum field theory, when you study quantum field theory in the 6th grade, and people said, what is a particle? They said it's an irreducible representation of a Poincare group. But the expanding universe is not Poincare invariant. There's a time dependence in the expansion of the universe, and the notion of a particle is approximate. So the cosmological expansion leads to a time-dependent Hamiltonian, which mixes, in the language of Schrodinger, incoming and outgoing waves, positive and negative frequency modes, which leads to particle production. So the expansion of the universe provides an arrow of time, breaking Poincare invariance and leading to particle creation. Now, as I mentioned, there exists a standard inflationary picture, but not a standard inflationary model. But for the most part, for the calculations, I will use a simple inflationary model, which is a single field with a quadratic inflaton potential, which is a mass mu. So that's a simple potential. This is a simple model that is unfortunately ruled out by observations. These observers rule out nice models that we have. It's not fair. You know, we can spend all morning coming up with a model, and the observers spend 10 years of their life in launching a satellite to disprove the model. So they'll come in my office and say, I disproved your model. I said, okay, come back in 10 minutes, I'll have another model for you. So this is ruled out by observation, but what the CMB observations do is to study the inflaton potential at large values of the field, and I'll be interested in the inflaton potential around the minimum of the field. So it could be that it's ruled out up there, but you know, taking a quadratic approximation to the inflaton potential may be an accurate approximation for what I'll do. It's simple. It's ruled out by observation, but may be adequate. Okay, so I have 2 slides of sort of technical basic quantum field theory. So let's look at the Lagrangian for a free scalar field, which is not the inflaton, some simple free scalar field. There's a kinetic term and a mass term, and this is the Lagrangian in Minkowski space. If we promote this to a curved background, to curved space where gravity enters the picture, then, which was hidden on the previous slide, is the Minkowski metric. But if we put in the actual space-time metric, G mu nu, it enters in there in yellow. And now we can add a non-minimal coupling to the Ricci scalar. C is some constant, R is the Ricci scalar. Now, in the language of effective field theory, this is a dimension 4 operator. There is no reason to exclude it from the Lagrangian. No reason to include it, but there's no reason to exclude it. And the point of view is, in quantum field theory, anything that's not forbidden is compulsory. That's also the approach of anybody have high school children. You know, if it's not absolutely forbidden, you have to do it. So this is something that we, in principle, have to add. So then you go through some steps, finding a canonically normalized scalar field. So this is phi, that's not the curly phi, related to the scale factor A in conformal time. And it looks like sort of a simple Lagrangian. There's a time derivative, a spatial derivative, and the only difference is that the effective mass squared is time dependent because of the expansion of the universe. So the effective mass depends upon the scale factor A, and if C is not equal to 1/6, it depends upon the Ricci scalar. So the cosmological expansion leads to a time-dependent background, which leads to a time-dependent Hamiltonian for something that's known as a spectator field. This is a field that's not affecting the stress energy tensor that's dominated by other fields. It's just a spectator going along for the ride. It's a semi-classical calculation. The field is quantized, but the gravitational background is classical. So then you would go through in the usual quantum field theory 101 method and find the Fourier, do a Fourier expansion, creation and annihilation operators, et cetera, and you find a mode equation for the Fourier modes of the scalar field, chi sub k, that just looks like the standard wave equation, except the frequency squared depends upon time, conformal time eta, because the expansion of the universe depends upon time, and there's an effective mass squared that depends also upon the Ricci scalar. Okay, so this is the last technical quantum field theory slide. I'm lying to you, there'll be more, but I don't want to scare you too early. So the solution of the wave equation include both positive and negative frequency terms for the mode function. So I can write a general solution to the mode equation as positive frequency terms proportional to alpha sub k and negative frequency terms proportional to beta of k. And let's assume we start with only positive frequency modes. So alpha of k is 1, beta of k is 0. That will be a solution to the mode equation if these terms in square brackets is equal to 1. So the term in square bracket departs from 1 roughly proportional to something that's known as the adiabaticity parameter, which is the derivative of the frequency divided by the frequency squared. So if that is much smaller than 1, the positive frequency solution remains a good solution. If this adiabaticity parameter is larger than 1, it's mixing positive and negative frequency terms. And in the Friedman-Robertson-Walker background, this is the solution to for the adiabaticity parameter. And if C is 1/6, this is known as conformal coupling, and the adiabaticity parameter will be proportional to the mass squared. So if you want to have gravitational particle production, you either have to have a non-zero mass or C not equal to 1/6. This is where bioconformal invariance is violated. Okay, so another physical picture of what's happening. The expansion of the universe causes an explicit time dependence in the action for spectator fields. An initial quasi-de Sitter early time vacuum may not evolve to a final Minkowski late time vacuum, but to an excited state populated by particles. And for quantum field theory, everything is oscillators. So imagine a simple quantum mechanics problem where you have a simple harmonic oscillator that you're varying the spring constant. So if you vary the spring constant adiabatically, very slowly vary the spring constant, the wave function will remain the same. But if you abruptly, non-adiabatically vary the spring constant, then you're going to produce an excited state of particles. This is the standard WKB calculation in quantum mechanics. So this non-adiabatic expansion, changing the spring constant, changing the mass, is related to the adiabaticity parameter. Okay, so that's the mode equation, omega k squared. I've written a couple of times. The Ricci scalar is negative in quasi-de Sitter space, so omega k squared is less than 0. And this is possible for minimal couplings where C is equal to 0. So looking at the mode equation, if omega k squared is negative, then you expect a growth for imaginary frequency. Omega k squared being negative, the solutions are no longer oscillatory, they are exponential. Then there's questions to ask particle physicists. So why should this coupling constant C be constant? There should be a renormalization group flow for C. You might set C equal to 0 or 1/6 at some scale, say the Planck mass. At other scales, there should be log corrections. I will assume it's constant. So conformal C equal to 1/6 and minimal C equal to 0 couplings are very different. This is what the frequency squared, the absolute value of the frequency squared looks like in the expansion of the universe as A changes, and AE is the scale factor at the end of expansion. So this would the end of inflation. This would be the end of inflation. So if omega squared is larger than 0, for conformal coupling, this is an example in the black curve of what the frequency squared looks like, the absolute value. If omega squared is less than, if you have minimal coupling, C equal to 0, you can have regions where the frequency is positive, regions where the frequency is negative. And during this negative frequency region, you expect a growth in chi. All right, so again, abrupt changes in the expansion rate leads to non-adiabatic changes in the frequency, which adulterates positive and negative frequency modes, leading to particle creation in the expanding universe. The non-adiabaticity parameter is proportional to that expression. And you see, you would be adiabatic deep in the quasi-de Sitter phase at the beginning of inflation, adiabatic at late time in approximately Minkowski. So you can define particles at the early time and at the late time, but in the intermediate time, the definition of particles is ambiguous. And the expansion becomes non-adiabatic if it's conformally coupled if C equals 1/6 at the end of inflation for sub-Hubble radius modes. If C is equal to 0, it can become non-adiabatic during inflation, producing super Hubble radius modes. Well, you have a differential equation. You need initial conditions. And the initial conditions, if you look at omega k squared, as a goes to 0, as a scale factor goes to 0, it just goes to k squared. And this motivates something that's known as the Bunch-Davies initial condition, which is also just a Minkowski space solution for the mode function and its derivative, the usual expression in the wave equation of 1/2 momentum, e to the minus k eta. This is a pure incoming wave. So as a goes to 0, the physical momentum is much larger than h. So you're looking at length scales much smaller than h, which should not feel the space-time curvature. So I make no apologies for the initial conditions. Okay, so again, you can write the wave equations, including both positive and negative frequency terms. And if you start with only outgoing waves, alpha equal to 1 and beta equal to 0, it will generate incoming waves. And the co-moving number density of particles at late time is proportional to this Vogel-Lyubov coefficient. And I will show some graphs where this is the spectral density of particles produced as a function of momentum k. So here's a simple evolution for conformally coupled scalars. If c is equal to 1/6, I've made a choice for the value of the mass of the spectator field divided by the expansion rate at the end of inflation, and a choice for the momentum k. Omega k squared for the co-moving, for the conformally coupled case starts as k squared at small a, and then grows as proportional to a squared for large A. The middle panel is the evolution of the adiabaticity parameter, and you see it becomes of order 1 toward at the end of inflation, A over AE of 1. This is the spectral density for this mode multiplied by 10 to the 8. And you see you start with no particles in the vacuum at early time, but at late time you excite the vacuum and you end up with particles. So this is a numerical result. I just love these figures. They're pleasing to me. It starts at 0, bounces around and goes to some finite value. Then this is from one value of the momentum, and then you integrate over the momentum and you calculate the total number of particles produced. This is the co-moving number, NA cubed, as a function of the mass of the particle divided by the expansion rate. And you see it decreases at small mass because for conformally coupled particles, you only break violent variance because of the mass. So as the mass goes to 0, the number of particles produced goes to 0. And it peaks at around the value of the inflaton mass and then exponentially decreases. This is the result conformal coupling, and for minimal coupling, the result is much different. It's even more interesting, the evolution of the spectral index. So for small mass and momentum, then it's non-adiabatic deep in inflation when the modes become tachyonic, and you have a suppression in the spectrum for large momentum and large mass. So this compares the spectrum for minimally coupled, C equal to 0 as a function of the mass divided by the expansion rate at the end of inflation, shown in red for small mass, for black for mass equal to 2, and blue for the mass over HE larger than 1. So you can either have a red spectrum, a flat spectrum, or a blue spectrum, depending upon the mass. And in purple here is the result of conformal coupling. So you see the spectrum diverges in the infrared if the mass over HE is less than 2, And this will lead to issues in the isocurvature modes of the CMB. So what is the great cosmological significance of particle creation? During inflation, the potential energy, the zero momentum mode of the field dominates, which leads to an acceleration of the universe. Schrodinger's alarming phenomena produces inflaton particles if it's a quantum effect, if h bar is not equal to 0. And the particles are produced with non-zero momentum. And this leads to inflaton perturbations plus scalerometric perturbations for a minimally coupled scalar field. So particles produce when they cross the Hubble radius during inflation, fluctuations on all scale, which with approximately the same amplitude, approximately the Harrison-Zodowitz spectrum. So the inflaton field is dominating the energy density, creation of particles, gravitational particle production, produces inflaton particles of non-zero momentum, which contribute to the energy density and lead to the primordial seeds of structure. So this is something that's well known and well studied. You start in a primordial universe with small seeds of structure, and over time, gravity is a free market force. The rich grow at the expense of the poor. It's a free market force, according to my economic friends. I don't have any friends who are economists at Chicago, but Chicago is a big center for economics of free market. And the rich grow at the expense of the poor. Regions that are rich in density grow at the expense of regions that are poor in density. So if you look out over Bologna, no, it's not Bologna, at Chicago. If you look out on the sky at Chicago, and if you had eyes sensitive to microwave wavelengths, you would see fluctuations in the microwave background that's studied by so many people here. So what you're seeing in this is a pattern of vacuum quantum fluctuations during inflation. So Schrodinger's alarming phenomena is responsible for the fluctuations in the CMB. If you imagine h bar going to 0, turn off quantum mechanics, because you never liked quantum mechanics when you studied it, the fluctuations would go away. You wouldn't have fluctuations in the microwave background. What would Fabio do without fluctuations in the microwave background? I don't know. And in fact, not only would you not have fluctuations in the microwave background, you wouldn't have fluctuations in the matter density, so you wouldn't have anything. So the thing to remember is that you are an amplified quantum fluctuation produced during inflation through Schrodinger's alarming phenomenon. So this is something that many people are looking for. Not only do you produce the well-studied temperature fluctuations, but the metric would have fluctuations also. So you can expand the metric as something that's a background metric, g mu nu 0, plus fluctuations in the metric, h mu nu divided by the Planck mass. And the field equations for the transverse traceless component of h mu nu is the same as what we've been studying for the massless minimally coupled scalar field. So gravitational particle production produces gravitational waves during inflation, and this affects the CMB temperature and isotropies. And there's a great deal of effort by my friends at Chicago who operate the South Pole Telescope, looking for the fluctuations due to the tensor fluctuations of the gravitational waves in the background. And also, I understand there's some satellite being planned, Lightbird, that will also look for the gravitational waves. So the gravitational particle production leaves an imprint during inflation, the Big Bang plus 10 to the minus 35 seconds, through quantum fluctuations, end up producing the CMB fluctuations, density perturbations, and gravitational waves that we look out in the universe at the effect of CMB and try to disentangle that. What more could gravitational particle production produce? Well, there's the issue of dark matter. We don't know the nature of dark matter. It's seen in many scales: cluster dynamics, galactic rotation curves, dwarf galaxies, gravitational lensing, nucleosynthesis, cluster gas and X-rays from the background radiation, structure formation, cluster decision. There's dark matter in the universe. What is the origin of dark matter? Well, for the last 40 years or so, the leading dark matter candidate is a weak scale cold thermal relic that most people refer to as a WIMP. The mass of the WIMP historically has been considered to be in the GeV to the TeV range, with weak scale interactions with the standard model and no self interactions, produced by freeze out from the primordial plasma, cold dark matter. And the great idea about this, the great aspect of this idea is that it can be detectable so many ways: by direct detection, looking in underground experiments; indirect detection, looking for annihilation, say in the galactic center; looking for the decay products of the WIMPs, and producing them at colliders. So there are all these ways to look for them, but unfortunately, in my opinion, it has not been seen yet. It's not been seen in direct detection. Now, if I was in Rome, I would talk about the Gamma Libra excess, but I won't mention it here. In indirect detection, there's a galactic center excess, but I don't think that's dark matter. In the decay of dark matter, some people claim there's a 3.5 keV neutrino that decays, that produces gamma ray lines. And in colliders and accelerators, there's no beyond the standard model signal. There are a couple of things that's not understood: muon G-2 at Fermilab, the mass of the W at Fermilab. There's some indication that it's not explained by standard model physics, but I don't think it's seen. So the idea I'd like to leave you with is that dark matter, if it's not a WIMP, what is it? There are many other possibilities: neutrinos, axions, asymmetric dark matter, sterile neutrino dark matter, the axino, self-interacting dark matter, inelastic dark matter, QBALs, or other solitonic dark matter, quark nuggets, hidden sector dark matter. I've worked on many of these ideas. But now, what if dark matter interacts only gravitationally? What is the one thing we know about dark matter is that it has gravitational interaction. What is the only thing we know about dark matter? It has gravitational interaction. Well, what if dark matter interacts only gravitationally? Then gravity must play a role in cosmological production, but gravity's weak. How can we use gravity to produce dark matter? And this is where gravitational particle production comes in. It can make very massive dark matter particles that has been called WIMPzillas, very big WIMPs. So a WIMPzilla is a very massive dark matter candidate produced via gravitational particle production. And by very massive, I mean it's too massive to be cold thermal relic. Its mass is much larger than 200 TeV. So let's make friends with WIMPzillas. This is something I've been working on for a very long time. These are some of my collaborators. I've been doing this probably for 20 years. 20 years or so. And I've worked with many students, postdocs, collaborators on this idea. And let's go back and look at the idea of conformally coupled scalar Wimps-Zilla as a dark matter candidate. Let's say we produce a massive particle that's stable with a mass comparable to the inflaton mass. Well, you can do a simple calculation to calculate omega h squared in the particle produced gravitationally. It depends on the ratio of the mass of the particle to the expansion rate of the universe at the end of inflation, depends upon the expansion rate of the universe at the end of inflation and the reheat temperature. Now, we don't know h sub e, we don't know the reheat temperature, but 10 to the 12 GeV for h sub e and 10 to the 9 GeV for the reheat temperature are common choices. Doesn't mean it's right, it just means it's something that most people assume. So if you can produce the co-moving number density Na cubed, that's 10 to the minus 5, you would be a candidate for dark matter. So here is something that's interesting to me. 10 to the minus 5 would predict a value of the mass of the particle divided by the inflaton mass that's about equal to 1 to cosmological accuracy, somewhere between 10 to the minus 2 and a few. This wouldn't work for minimally coupled dark matter because if the Wimps-Zillas contribute to the matter density, there will be two sources of density fluctuations: curvature fluctuations from inflation and fluctuations in the field itself, the spectator field, and these are uncorrelated. So inflation produces curvature fluctuations and also fluctuations in the dark matter field. And the dark matter density perturbations are uncorrelated with baryon and photon perturbations. And for a red spectrum, there are strict CMB limits that we look for. The observers always rule out interesting models, Planck and WMAP and other observations rule out isocurvature perturbations to a very good result. Let me skip this. Yeah. Okay, yeah, I'm almost at the end. So gravitational particle production in dark matter, inflation indicates a new mass scale. And in most models, the mass of the inflaton is approximately equal to the expansion rate during inflation. So the expansion rate during inflation is detectable via primordial gravitational waves in the CMB. And some of my colleagues tell me that in the next round of experiments, either in CMBS4 or Lightbird or other type of experiments, we're just on the verge of detecting gravitational waves, right? Fabio, right? Any day now, Fabio will announce it. So there's a mass of the inflaton. So it could be that there's a mass of the inflaton and there's only one particle, the inflaton, with a mass comparable to the mass of the inflaton. But that's not the way physics has traditionally been revealed to us. Once we discover a new mass scale, there are many other particles with mass comparable to the mass scale, to that mass. All of these particles would be produced by Schrodinger's alarming phenomenon. If the lightest of these is stable, it could be the dark matter, which is a Wimps-Zilla. So let me skip ahead to, so I talked about scalar fields, but of course there's vector fields, fermionic fields, spin 3/2 fields. But finally, let me get to the summary. My summary is that gravitational particle production can make dark matter and constrain beyond the standard model physics. Dark matter might have only gravitational interactions. That's all we really know. If so, dark matter must have a gravitational origin, and cosmological gravitational particle production through Schrodinger's alarming phenomenon is promising. For scalars, conformally coupled scalar fields is a promising dark matter candidate if the mass is approximately equal to the expansion rate at the end of inflation. Minimally coupled is not a promising dark matter candidate. To me, it's not promising. Dirac fermions look similar in the mode equation to conformally coupled scalars, and so it's also a promising dark matter candidate. Vector fields, massive vector fields, de Broglie-Proca Lagrangian vectors is a dark matter candidate, could be very light, a micro electron volt, or very massive. Spin 3 has Rorita-Schwinger fermions is something we looked at, and there's some interesting things that happen there that are relevant for supergravity. Catastrophic production, the sound speed will vanish, and this has implications for models of supergravity. Spin 2, Fierz-Pauli tensors. We're also looking at that now, and some of my friends are looking at spins greater than 2. Okay, so I'll leave you with a question. Some particle physics models that you could write down that's perfectly reasonable in Minkowski space lead to problems in a Friedmann-Robertson-Walker background. So what do we make of a quantum field theory that is perfectly reasonable in Minkowski, but pathological in a Friedmann background? Examples are Fierz-Pauli fields, spin 2 with a small mass, scalar fields that are minimally coupled. All right, so you're so excited about hearing this, you can't wait to learn more. Coming soon to a reviews of modern physics near you will be a review article, a long review article that I'm writing with Andrew Long that should be done, if Andrew is working hard while I'm here enjoying Bologna, in a couple of months. So that's my story of gravitational particle production in the early universe. Thanks for your attention.
Thank you very much. Is there any question from here or from online?
Yes. So thanks for this colloquium. Very nice, and it's a nice topic. So you spoke about the expanding universe. Would you have other region of strong gravity where you could create this